What's up, guys? Grayson here with another based theory. What actually is energy? Many people have an intuitive, often spiritual or vibes based understanding of energy. Some might say a certain place has bad energy, and we all have some idea of what that means. Many people would echo what they've learned in middle school. Energy is the ability to do work, and we'll definitely be returning to that definition later. But when most people imagine the words pure energy, there is a certain amount of overlap in what they generally are thinking of. Usually it's some sort of light, whether a glowing aura, or a sphere of light, or a beam, or bolt of electricity. Some might even think of an explosion as pure energy. We all have some kind of notion of energy in its most raw, fundamental form. Some might even say that people have their own energy that carries forward after they die, a soul. But what exactly can science tell us about what's really going on with energy? The first law of thermodynamics tells us that energy cannot be created or destroyed, only transformed. Chemical energy to heat energy to kinetic energy to electricity, all these forms of energy are in many ways emergent phenomena. And ultimately, they can all be broken down into just two basic forms of energy: kinetic and potential. What we feel as temperature and heat energy is actually just the macroscopic effect of the microscopic kinetic energies of all of the molecules in that area, as they physically collide and bounce off of us and each other. Even light has kinetic energy, and it can use its momentum to push spaceships on solar sails, like wind does with regular sails in the ocean. This was first done in 2010. Now, kinetic energy makes intuitive sense to most of us. A punch delivers its energy because it is a certain mass moving in a certain velocity, and bam! Potential energy, though, isn't quite as intuitive. And light is massless, so how can it have kinetic energy? Well, the real story is a little more complicated. When I first learned about kinetic and potential energy, it never really felt like there was a clear way to wrap my head around what potential energy really is. I mean, how is an object on a shelf any different than the same object on the floor? Sure, one has a higher potential to move than the other, because if the shelf were removed, the object would fall. Ultimately, though, that just seemed like kinetic energy being gained to me. And it was easy for me to think of gravity as having done the work, and thus supplied the energy to the object, giving it kinetic energy. But no, that doesn't make sense, because that would mean that every time something falls to Earth, the gravitational energy of the Earth would be decreasing. And we know that isn't the case, as gravity only depends on mass. So, where does that kinetic energy come from? If it's from the object on the shelf's potential energy, what does that mean? To figure this out, we're going to have to get quantum. See, most people think of light when they think of pure energy. And light is not a bad place to start. Einstein taught us that mass and energy are really just different forms of the same thing, related by the famous equation E equals mc squared, meaning that mass can be converted to light energy and vice versa. And just like what we saw with heat energy being a macroscopic effect of individual molecules, the light that we see is just an additive result of individual photons. So, if light is made of discrete units, then what's a photon made of? That would get us even closer to understanding what pure energy really is, right? Well, photons are a fundamental particle, meaning that in the standard model of particle physics, they are not made up of any smaller parts. So, what is it? Well, in quantum field theory, the fundamental particles are quantized excitations of a quantum field. A photon is a discrete excitation of the electromagnetic field. An electron is an excitation of the electron field. And a quark is an excitation of the quark field, etc. Every fundamental particle is an excitation of a fundamental field. So what are these excitations? What shape are they? What makes them up? Well, in quantum mechanics, particles are described by wave functions, which are mathematical equations that relate certain properties about the particle, like its position or momentum. Schrodinger's famous equation, one of the pillars of quantum mechanics, describes how these wave functions change over time. Every quantity that you could ever want to know about a particle can be calculated in this way. So the wave function really is a complete picture of what a particle is and how it behaves. There are not particles or waves. There are wave functions, which themselves describe amplitudes and flow. The debate about whether these wave functions represent actual physical phenomena that are really happening is not yet settled in science. Some scientists and theories agree that they are physically real, while others say there is no physically real analog for the behavior described in the wave function. It is, after all, a complex function which describes flow both in real and in imaginary dimensions. So, whatever it is describing has symmetries and behaviors that are very difficult for us to conceptually grasp. However, when we multiply the wave function by its complex conjugate, the imaginary terms cancel out, and we are left with a description of the particle using all real numbers. And it allows us to calculate the three-dimensional shape that the particle is distributed within, known as the probability density. The probability interpretation was introduced by Max Born and is part of the standard Copenhagen interpretation of quantum mechanics, stating that the shape of the probability density shows us the probability of finding the particle in a particular location. And the Schrödinger equation shows us how these probability densities change and flow over time. But here's the really interesting part. You see, the modulus squared of the wave function is not just a description of probability density. It is an energy function, and can equally be said to describe the shape of the energy density of our particle. Since these are energy equations too, we can just as easily do away with our conception of particles being these little point-like billiard balls and think of these shapes as the three-dimensional distribution of energy density for our particle, knowing that the particle has a higher chance of being measured in areas where its energy is more dense. The particle is not just a point in space, but a description of how the wave function interacts in a point-like way. But the particle itself is smeared out across space. Its energy density is spread out in shapes described by the square of the wave function. So, we've now found the shapes for the most fundamental form of energy, fundamental particles. All of the different types of energy we spoke of at the beginning of the video can be broken down into kinetic and potential energy, which are both described by the wave functions of fundamental particles. All forms of energy can ultimately be described in this way. Well, besides dark energy, but that's still a huge mystery we don't know enough about and is a totally separate topic and a video for another day. The wave function of a particle can describe both the potential and kinetic energy states of the particle. And here's the real kicker. You see, there will be an actual difference between the wave functions of an electron on the floor and an electron on the shelf. Changes in potential energy do have an actual calculable change on the wave function of a particle. In quantum field theory, both changes in potential energy and changes in kinetic energy actually change a particle's wave function. All changes in energy change the particle's wave function. To bring back that middle school definition of energy as the ability to do work, we have just seen that all changes in energy necessarily entail changes to a particle's wave function. So the work described is really the work that it takes to change the wave function. And all energy ultimately boils down to the ability to alter the wave function. So when you punch someone, You are physically changing quantitative aspects of all the wave functions of all of the particles in their phase. So, what should we visualize when thinking about energy? The shapes of probability densities for fundamental particles can tell us how energy is shaped and distributed in space. But it's still a little unclear. Thinking about it as light is not quite right though, since we know that light is just made of photons, so on this quantum level there wouldn't be any light to see. The way I personally like to think about these shaped excitations of fundamental fields is to think of a different kind of field excitation. Now, when you put two magnets together, you can feel the magnetic field between them as a force of attraction or repulsion. That repulsion is a real physical force that you can feel between the two magnets. And it is the feeling of this force which I use to conceptualize the excitations of fundamental fields, rather than any visual notion of light. You can think of particles as that feeling of the force you feel with a magnetic field, only extremely small and bent back on itself and tied into a knot with the shape described by the wave function. Ultimately, our mathematical descriptions of these fundamental particles describe them in terms of symmetries and harmonics, which lends itself to thinking of them as discrete harmonic loops of energy density. Ultimately, though, our notions of energy are only relative. Kinetic energy only makes sense based on comparison to a frame of reference. A bullet has a different energy relative to the person who fired the gun than it does relative to an observer on a nearby train. Something only has kinetic energy or potential energy relative to some other point of comparison. This is a very spooky topic if you think about it, because it calls into question what exactly the absolute value of any of these energies truly are. Whether there can even be any meaningful understanding of what energy is if there's nothing to compare it to. For example, if every point in the universe had the exact same energy, then it would not be meaningfully different if every point had zero energy. No matter what energy level each point has, as long as they are the same, there is no ability to do work in such a universe. This touches on the mysterious zero-point vacuum energy that pervades the universe like a constant background of television static that's described in quantum mechanics. And it has even caused many scientists to speculate that, as counterintuitive as it may sound, that the total energy of the universe may just add up to zero. Thanks for watching, guys. Sorry if you're more confused now than you were when we started, but such is the nature of fundamental physics. Hopefully, this based theory has given you some new and interesting things to think about. Let me know what questions you have or how you think about energy in the comments, as well as any topic you'd like to see me cover in the future as another based theory. Till next time, remember, like, share, and subscribe for more.